Well, welcome everyone to this introduction to matrix algebra. A number of you will find this material very basic, but a number of you will also find this material maybe somewhat new. So this lecture or set of notes here is geared towards those students who come into this class without much of a matrix algebra background. I hope that this set of notes then helps those types of students. Of course, after watching this lecture, if you have any questions, please feel free to ask me your questions. Okay, so the very basics then. Well, what is a matrix? It's simply a way to group numbers or symbols together into what you could say is a rectangular array where you have rows and you have columns of these elements or items inside the matrix. So, for example, here, let me get out my red pen. What we have is a simple matrix. It has the numbers 1, 2, 3, 4, 5, 6 in it. It has 2 rows. It has 3 columns. And so because of that, we say the dimension or size of the matrix is 2 by 3. Okay. Now, that's an example of a matrix with numerical values in it, but we can also use symbols when we want to be very general. So I could define a particular matrix, which I call A, and notice here how I have a bolded letter. Typically, when you're working with matrices, you always bold a letter or symbol that denotes a matrix. This matrix is also 2 by 3. And to denote its elements generically, I just simply use little a's here. Where notice the first letter here, the first number in the index here is the row, and then the second number is the column. This is standard notation in matrix algebra. The first index is always the row, second index is always the column. So for example, a sub 2, 3 is row 2, column 3's element. In a more general sense, we can also have a matrix that's of size, let's say R by C, and that's what's shown there in that illustration. In this class, we will often be working with square matrices. So, for example, if you've heard of a covariance matrix, that's always a square matrix. And a square matrix has the same number of rows as it does columns. So let's take a look at an example that you're familiar with and put it into a matrix algebra context. So in the introduction to R notes that we saw before, we saw this high school and college GPA data set where we want to use high school GPAs to predict college GPAs. We had a sample size of 20. Well, we could put all the high school GPAs into a matrix. And that's what I did here. I decided to call it my X matrix. Often people will verbally call this a design matrix in other settings. And what I have here is all the high school GPAs are shown in column 2. And then we also have a column of 1s as let's say, the first column in that matrix X. If you don't know why I have a column of 1s there, don't worry about it. You'll see why that occurs shortly. But what we have here is a 20 by 2 matrix. So 20 rows because we have 20 observations in our data set, where the first observation had a 3.04 high school GPA, the 20th observation had a 1.88 high school GPA. A special case then of a matrix is called a vector. So if I simply just looked at one column here of my X matrix, I could consider that to be what's called a column vector. I could also do that with this set of 1s there. This is one column vector. Also what you could do, let me do some erasing here, is look at just maybe one row. And this is what's called a row vector. So a row vector in general is 1 by C, meaning it only has one row to the matrix. And a column vector is R by 1, meaning it only has one column to the matrix. So, for example, a symbolic representation of a 3 by 1 column vector is something like this. Notice here how I have dropped the column number because we know that there's only going to be one column. In the context of the high school and college GPA data set, we're going to be dealing with a Y vector, and this basically just means that we're going to put all of our college GPAs, all of our Y's, into a 20 by 1 matrix, which again we call a vector for short. Now sometimes we like to be able to rearrange the elements that are inside of a matrix, and we can do that by doing what's called a transpose. Simply that means is you interchange the rows and the columns of a matrix or vector. So for example, here's my original matrix A that we had before. And when I put this little tick mark there, or apostrophe, we actually call this a prime. That's the standard notation or standard wording in matrix algebra. If I put that little prime mark there, meaning now I have A prime, what that essentially means is I have a transpose of A. So I'm going to take the first row, now make that my first column. I'm going to take the second row and make that my second column. So A was a 2 by 3 matrix. A prime is going to be a 3 by 2 matrix. In other contexts, or let's say other books or other classes, sometimes you will see this notation where you have an A with a superscript T next to it to mean transpose. Also, I should point out, this was actually before in the notes, when someone actually just writes out a matrix, like on a chalkboard or whatever, when you can't necessarily, let's say, bold it to make sure that people know it's a matrix, often what people will do is take an A, let's say if that's my matrix, and simply draw a line under it to mean the bold A, which means then in our context a matrix. Just a second here. Okay, so then, sorry, my computer's a little slow right now. So with respect to the high school and college GPA data set, we might want to make my column vector a row vector. So Y prime is a row vector, a 1 by 20 matrix. Now, just like how you do with regular old numbers, you might want to add and subtract matrices. And it's a very simple thing to do. All you do is you add and subtract the corresponding elements of the two matrices that are of interest. So if I had this matrix A and this matrix B here, if I want to add the two matrices together, I just simply take 1 plus -1, I get 0. I take 2 plus 10, and I get 12, and so on. If I want to subtract the two matrices, then I can take 1 minus a -1 to get a +2. So notice then with this kind oops, hold on here. So notice when you do matrix addition and subtraction, you need to make sure that the matrices are exactly the same size, same number of rows and same number of columns. So let's take a look at how we can do some of this stuff in R. My corresponding R program then is this basic _matrix_algebra.r. You can download this from my corresponding course website, of course. Let me go over here to 10. Okay, let me just make this a little bit bigger too. Sorry, I forgot to do this before. Okay, so I like to first create a matrix A. And to do that, I can say A gets, and then I use the function matrix. Makes sense? What am I going to put in my matrix? I'm going to put some data. So my data, I'm going to combine the numbers 1, 2, 3, 4, 5, 6 together. So notice I highlight that code and run it, you can see how they were combined together. Let me also make this a little bigger too. And I like to put all these numbers that we see there in data into 2 rows and 3 columns. And the way that I'm going to put them into the matrix, I'm going to do it by row. Meaning, let's run this and see what happens. I took 1, 2, 3 and put that in the first row. I took 4, 5, 6 and put that into the last row. Now look what happens though if I would have done the default of false here. Again, this is the default. Notice that R puts 1, 2 into the first column, 3, 4 into the second column, and 5, 6 into the last column. So you always got to be careful whenever you're creating a matrix that you know the ordering that items are put into the matrix. Okay. Now also, if you remember from the Introduction to R class, every object in R has a class. Well, what's the class of A? It happens to be called matrix. It didn't have to be called matrix. It's just in the matrix function itself, the people who've written it have designated that anything that's created with the function matrix is going to have a class of matrix. Here's my B matrix as well. Notice how I have everything here on the same line. You can do that, or you can do it just how I did before. With this matrix A, the reason why I had done it like as in this case was to help you see what goes in the first row and what goes in the second column. It doesn't matter if you want to do it or not. So here's my matrix B. If I just type B, you can see the actual matrix there. And let's do some addition and subtraction. So I take A plus B and A minus B, and you get as you would expect. Okay. So we already talked about the first note here. We talked about the second note. Let's talk about the third note. This is can be a little bit confusing. I'll point out other situations later why this is important to understand. So don't worry if you don't get it the first time why I'm making this differentiation here. Okay, so if I want to, I create a vector using the matrix function, because after all, in a mathematical context, a vector is a special case of a matrix. So if I want to create a y vector, let's say that is in this case a column vector, has 3 rows and 1 column. I can simply do it using the matrix function. It has a class of matrix. But instead, also what I could do is create a vector called x and just simply combine the numbers 1, 2, 3 together, and I get x out like this. Notice though how the output looks a little bit different between the two cases here. That's because R is actually treating them differently. The class of x is called a numeric. In R's terminology, R differentiates something called a vector from a matrix. And again, that's where it can be a little bit confusing. And whenever I create something like this with the C function, this is actually what R calls a vector. Now you can often work with vectors and matrices in the context of what R calls them. We can work with them interchangeably, but you just have to be careful on some things, and I will point out those things shortly. We can also do a transpose of a matrix as well. R has a function T that actually finds the transpose. So just like how you've multiplied regular numbers together, we can also multiply matrices together as well. But let's look at the simplest case overall first, where we multiply a matrix by a single number. In matrix algebra terminology, people often use the word scalar to mean a single number. In other words, a one-by-one matrix. So if I want to multiply my matrix A by a single number, a scalar, let's just call it C here, all you would need to do is take every element of your matrix A and multiply it by C. So for example, if this was my matrix A here, and I wanted to take A times 2, all I would do is take every single element of A, multiply it by 2. Really simple. Now, if you have two matrices that you want to multiply together, it becomes a little bit more complicated, especially if you haven't ever seen this before. So let's say I have two different matrices. Let's just call them A and B. If I want to denote their multiplication, I could very simply use A asterisk B if you really wanted to. Or what you will see more commonly done is just the two letters written next to each other. So I would read this as A times B. And in order to multiply two matrices together, you need to have the following hold true. The number of columns of A needs to be the same as the number of rows of B. So for example, if A was a 2 by 3 matrix and B was 3 by 10, you could multiply these matrices together. However, if B was something else, where the number of rows wasn't equal to 3, then you cannot actually multiply the two matrices together. And you'll see why that occurs shortly. So we know when we can multiply A times B, but what is the result? What does the resulting matrix look like in terms of size? Well, how about we call this resulting matrix C, just to be general. Well, the number of rows of C are going to be the same as the number of rows of A. Also, the number of columns of C is going to be exactly the same as the number of columns of B. So in a very general context here, if A had W rows, Z columns, B had Z rows, Y columns, notice how these two Z's are exactly the same, or we have the same letter there, so that means then the number of columns of A is equal to the number of rows of B. So we can do the matrix algebra. I'm sorry, the matrix multiplication, that is. But then look at the leftover indices, or leftover dimensions, you could say. Those become then the dimension of the resulting matrix C, W by Y. So to actually do the matrix multiplication, I think it's best explained through a simple example. So here's my A matrix that I had before with 1, 2, 3, 4, 5, 6 in it. And let's look at this particular B matrix. Notice that B is 3 by 2, A is 2 by 3. So since the number of columns of A is equal to the number of rows of B, we can do this multiplication, and the resulting matrix will be 2 by 2. Okay. So when I do the multiplication, what I'm essentially doing is what's called doing a cross product of the rows of A with the columns of B. So I'm going to take this first row of A and multiply these elements by their corresponding elements in the first column of B. So I'm going to take 1 times 3, I'm going to take 2 times 1, and I'm going to take 3 times 0. So you see that happening right here. And then I add them up. So 1 times 3 is 3, plus 2 times 1 is 2, plus 3 times 0 is 0. So I get 5. Notice since I had the first row of A, first column of B, that means I have the 1, 1 element of the resulting matrix C. Let's look at one more example to make sure it's clear. Let's actually use some highlighters. So now let's look at how I get this 7 here. This results from taking the first row of A and doing a cross product with the second column of B. So I take 1 times 0 plus 2 times 2 plus 3 times 1, and I get 7. That's how you multiply a matrix or how you do matrix multiplication. It's not too bad, but you can see that if we have any kind of large matrices, doing these by hand is not going to be a fun thing to do. So that's why we typically do it using computers. Now, it's important to note that in a very simple context, if I were to take 2 times 3, I get 6. If I take 3 times 2, I get 6 as well. However, now if I take matrices A times a matrix B, let's call that C, if I take B times A, I do not necessarily get the matrix C. Well, why? Let's take a look at this. So now notice how B is a 3 by 2 matrix and A is a 2 by 3 matrix. So because we have these 2's here, they're the same, we can do the matrix algebra, but notice the resulting dimension of the matrix is going to be 3 by 3. So for example, I take the first row of B times the first column of A, the corresponding elements, add them up, and you get 3. You do that throughout there, you see that we get a 3 by 3 matrix in the end. Of course, that's different from our 2 by 2 matrix before. Now, even if, let's just say, for example, let's say A was a 2 by 2 matrix and B was a 2 by 2 matrix. Obviously, then C is going to be a 2 by 2 matrix. Even if we had something like this happen where, if I were to take B times A, I would still get a 2 by 2 matrix. Unless these matrices A and B have certain properties to them, you're not going to get the same result in terms of when you do A times B and B times A. Try some examples on your own to actually see that. Okay. So then in general, for a 2 by 3 matrix times a 3 by 2 matrix, this is what you would get. Let's look at how we can do some of this stuff now in R. Okay. So I'm going to create my matrix A, create my matrix B. Let's do that. So here's A, here's B. Now if I want to take A times B, you might say, well, you might do something like this, A asterisk B. In fact, that's something you could do, for example, in SAS. However, that does not work in R. Instead, since we're working with matrices, we have to use this syntax. A percent asterisk percent B. So this part here in the middle tells R you want to do matrix multiplication. So we go ahead and hit enter there, and we can see that we get exactly the same matrix that we did before. I take B asterisk star, B percent asterisk percent times A. There we get the result that we got before as well. So you just got to be careful with your syntax that you use. Now, you might be wondering then, well, what does an asterisk do then in R? Well, it performs what's called element-wise multiplication. So, for example, let me create a matrix called E that just because it's easy, is exactly the same as A. Now, if I take A percent asterisk percent E, look what happens. Oops, didn't do it right. A asterisk E, that's what I was trying to do. What happens is that I have element-wise multiplication. So the first element of A, which is 1, taken times the first element of E, which is 1. So you take 1 times 1, I get 1. Let's look at the 2, 3 element, 6 and 6. 6 times 6 is 36. So in this particular case, notice that to do element-wise multiplication, you would need to have matrices of exactly the same dimension. But my main purpose of showing this to you is to show you, well, what does the asterisk do and how it differentiates from the percent asterisk percent syntax in R. Well, what about multiplying vectors with other vectors or matrices in R. This is where you need to be a little bit careful about knowing what you are doing. So for example, let's say that in a mathematical context, I create a vector called x, and it looks like this. It's a 3x1 vector, and I could use the matrix function R to define it. I could, but instead, just to illustrate, I'm going to use this C function instead. I'm going to put 1, 2, 3 together in what R would refer to as a vector. Now look what happens when I take x percent asterisk percent x. Or I'm just going to call it x times x because it's a lot easier to say that. X times x, I get 14 back. Well, wait a second. How does R know that I want to actually do what will be equivalent of x transpose times x? So in other words, it did this in a mathematical context. Oops, I don't need that. Sometimes when you have a vector, row vectors, it's easy to separate the numbers with commas, and I guess I'll do that for illustration purposes. So if I take these two vectors multiplied by each other, I get 14. But remember here, this x here does not necessarily have a row or column dimension in R's context. So equivalently, what I could have, what R could have done is interpreted what I wanted as x times x transpose. So in other words, this. Look at another example. If I take a times x, and remember a is a 2x3, and x itself doesn't necessarily have row and column dimensions at all in R itself. But in order to do this matrix multiplication, x needs to be 3x1. And in fact, it did it, and this is what it gets. Or did the multiplication, that's what it gets. So how does R decide how to work with a vector like this? Well, basically what happens is, in the context of a times x here, it's going to make this x vector, it's going to make it a matrix in R's not notation, but R's syntax is going to make it a matrix such that the matrix multiplication will work, can be done. So obviously x could not be a 1x3 in order for this to work. It has to be 3x1. So that's why we ended up getting this. Well, what about then the case of x times x? Well, in that particular case, since we have two vectors multiplied by each other, R will return what's called in a mathematical context an inner product. Simply x transpose times x, or x prime times x. That's what it will always return. If you wanted instead, let's say, x times x transpose, oops, sorry about that. This in a mathematical context is called an outer product. And you could do that in R by, instead of having an asterisk in the middle, have a O, lowercase o instead. We won't work with outer products in this class, so don't worry about that. My main purpose of showing you this here when we're working with what R refers to as vectors is, first of all, not to confuse you, but to make you think about what you're trying to do and make you think about, will a certain kind of matrix multiplication actually work or not? Okay. So let's go back to the high school and college GPA example once again. Now, when we do regression analysis with this data set in terms of matrices, we are often interested, and you'll see why shortly, in a few different matrix multiplications, such as x transpose times x, or x prime x, you could say. We're interested in x transpose times y, and y transpose times y as well. So let's do some of these in R. Excuse me. Let's first of all just simply read in the data, as we've done before. And then I'm going to use the head function. I've shown you this before. What this head function does, it allows me to look at the first 6 observations in any data frame that I have. It's a helpful tool in this situation here to make sure that I read in the data correctly. You could also use a tail function too to look at the last 6 observations. To create my X matrix, what I'm going to do is use a function called cbind. This means combine items by column. So I'm going to pull out my high school GPAs from my data frame, and I'm going to put that in the second column of a new matrix where the first column just has 1s in it. Now, of course, this high school GPA here has 20 items, and a 1 has, well, simply just one thing. Well, how does R then react when it sees something like this? It does what's called recycling, where it will recycle this 1 20 times so that a matrix could actually be formed with this high school GPA here. So what we end up having is a 20 by 2 matrix. And let's take a look at it real quickly. And you can see here's my X. It has 2 columns and it has 20 rows. I'm going to put all the college GPAs into a vector. This is a vector in terms of R's terminology, a vector called Y. And this is what Y then looks like after you print it. So let's take the transpose of X times X. So X prime times X. And this is what I get. So notice I only have 20 here. Well, remember, our sample size was 20. Well, why do I end up having the sample size there? Well, let's take a look at how the matrix algebra or matrix multiplication is actually done. This is on page 16. So X transpose times X. This is what it looks like. So X12 represents then the first row, second column of my X matrix. Xn2 would be the nth row, second column of the matrix. Notice how this is a transpose. That's why you see this as a 2 by 20 matrix. I take it by my regular 20 by 2 matrix for X. And so when I do this matrix multiplication then, which is erasing, again what I'm doing is I'm taking the first row times the first column, and I add up the corresponding terms. Well, I'm taking 1 times 1 plus 1 times 1, and I do that n times, and that's my sample size. So n was 20 in our particular case. I just happened to write out these X matrices in a very general context, putting n there versus 20, and so that's why we get an n there. Now look at some of the other parts of this matrix. When I take my first row times my second column, essentially what I'm doing is just summing up all the X's. Excuse me. Let me restate. I'm summing up all the high school GPAs. So the sum of all the high school GPAs then ends up being 51.38. The sum of all the high school GPAs squared is 148.46. When I take the transpose of X times Y, remember well, let's actually take a look at this again. Taking the first row of this X transpose times the column vector Y. Remember, these X's are 1s, so that's why I get the sum of the Y's. I can also do the same thing with the second row as well with this. Oops. With my column of Y's, and I get the sum of my high school GPAs times their corresponding college GPAs. Notice what happens with Y prime times Y. I get the sum of the Y's squared. And there you go. Just another way to get an X matrix out that might be a little bit easier than using the cbind. with the Introduction to R lecture, we looked at how to use the LM function. And if I were to use the LM function to estimate my model and put the results into an object called mod.fit, then I can use a function called model.matrix, and this gives me my X matrix out. Let's look at some special types of matrices that we will often see during the semester. First of all, we're going to look at a symmetric matrix. That just basically means if I have a matrix A and it's exactly the same as the transpose of A, then A is symmetric. So, for example, let me get my red pen out again. Here's my A matrix here. Now, if I were to take the rows of A and make them the columns of now A transpose, notice this is not changing my original A matrix. It's exactly the same. For those of you who've heard of a covariance matrix before, a covariance matrix is a symmetric matrix as well. We will have lots of covariance matrices that we will work with this semester. So that's why we need to know what a symmetric matrix is. Let's next talk about a diagonal matrix. First of all, well, what is a diagonal of a matrix? The diagonal of a matrix are the elements that correspond to when the row number is equal to the column number. So 1 and 3 lie on what's called the diagonal of the matrix. All the other elements of a matrix then are called the off-diagonal elements. So now a diagonal matrix then is a square matrix whose off-diagonal elements are all 0. So here's a 3 by 3 diagonal matrix. Here on the diagonal, we have possibly non-zero items. They could be 0 as well. But all the off-diagonal elements, as shown here, are equal to 0. These kinds of matrices will often appear, and we will often use them in our course. A special kind of a diagonal matrix is called an identity matrix, where now all these items on the diagonal are equal to 1. So why is it called the identity matrix? Well, simply, if I were to take A times I, where I is an identity matrix, let's say, and A is an appropriately sized matrix so that you can do this matrix multiplication, I will get A back. So essentially, it's just simply like if I were to take the number 3, take it times 1, I get 3. If I were to take the number 10 times 1, I get 10 back. So the number 1 there, in a regular multiplication context, now is extended to a matrix context through the idea of an identity matrix. Now, sometimes during the semester, we will sometimes work with vectors and matrices of 1s. So often a little j vector denotes a vector of 1s. A big J matrix is a matrix of 1, and that can help with some of our calculations. And I'll let you look at on your own, verify on your own that when you do some matrix multiplication here, you get those quantities as shown there. Sometimes it will be useful to define a matrix, or in this case, a vector of zeros. So here's a vector of zeros here, and notice how it's denoted with a bold 0. And in this particular case, as R rows, just to be general. Okay. So this takes us then to linear dependence in the rank of a matrix. This is going to pop up a few times this semester. Not a whole lot, but a few times. And it's just something that we need to be careful about, that we don't are not worried, that we don't have to worry about this linear dependence issue. So let's define a matrix A as you see on the screen there. I'm actually going to divide A up into 3 different parts where I have 3 column vectors, A1, A2, and A3. Now you'll notice that if I were to take then the second column here and multiply it by 3, I get the third column. So because of that, we say the columns of A are linearly dependent. one is exactly the same as the other if I just simply multiply by a constant. Now, there's actually a more formal definition of linear dependence. So let's say that we have a set of constants. Let's just call them lambda 1, lambda 2, down to lambda c. So this could be like the number 1, could be the number 0.5, could be the number -3, for example, any of these constants. And let's say that at least some of them are not equal to 0. Then you know that you have some column vectors that are linearly dependent if I were to take then this linear combination of the lambdas with the a's, if I were to get that to be equal to 0, I have linear dependence. So in the previous example here with the A matrix, suppose lambda 1 is 0. I take it times A1. Then I take, actually do this. Suppose I take -3, so -3 is lambda 2 times A2, and then I add A3. If you do that calculation, you get a 0 vector. That again shows that we have linear dependence there. Then the rank of the matrix is the maximum number of linearly independent columns. In this case, the rank of A would be equal to 2. Now, the reason why this linear dependence issue is important is because when we have linear dependence, it may prevent us from doing particular calculations. And when we come across that, we'll talk about that more later. Let's talk about how to find the inverse of a matrix. Now, all of you have seen cases such as, maybe I have the number 3, and I want to do what's called invert it. In other words, take 1 over 3. Now, if you were to multiply these two together, you get 1. Now, let's talk about this in the context of matrix algebra. So let's say I have a matrix A, and it has an inverse to it called A inverse. So that -1 in the superscript there means inverse, set as A inverse. Then if I take A times A inverse, instead of just getting the number 1 as we did before, now we're in a matrix algebra context, I'm going to get the identity matrix, which again we often just simply denote as I. Also, if I were to take A inverse times A as well, I will get I2. So that what this is saying then is that A has to be a square matrix. So whenever we work with inverses of matrices, we always have to have a square matrix. Let's take a look at an example. So here's my matrix A. It has simply 1, 2, 3, 4 in it. And then its inverse then is what's shown there. And you can verify on your own that when you multiply A times A inverse or A inverse times A, you get the identity matrix. Now, how did I find this A inverse? Well, in a 2x2 context, it's not too difficult to do. And that's the only context that you'll be responsible for when you get to 3x3, 4x4. The calculations are not fun to do if you're to do it by hand, so we just simply use computers. But in a 2x2 context, let's say that I just have this general matrix A here. A inverse then is as follows. Out in front, I have this constant where I'm going to take the diagonal elements, multiply them together, so A11 times A22, and then I'm going to subtract then the multiplication of the off-diagonal elements, A21 and A12. Then look what also happens. So I have this constant out in front. I'm going to multiply then by my A matrix with some things switched. In particular, A11 and A22, they're going to switch places. Also, I'm going to put negatives out in front of A12 and A21. Verify that on your own that indeed, if you were to take A times A inverse, you do get the identity matrix. Okay, so let's take a look at how we can do some of this stuff in R. Let me go over here to my R program again. So I'm going to create my matrix A. Now you might think there's probably this function called inverse that finds the inverse of A. Actually, there isn't. Instead, we have to use a function called solve. And simply, there is my inverted matrix. So that if I were to take A times A inverse, I get the identity matrix back. Of course, this right here, 1.11 times 10 to the negative 16th powers, practically 0. There's just some very, very, very small round off here, and so that's why you don't see it actually shown as 0. We could also do A inverse times A and get the same result back. Okay, so let's take a look at then the high school and college GPA example once again. Here's my matrix X, here's my matrix Y. And one very important use of the inverse, an inverse of a matrix in matrix multiplication in regression analysis is this right here, where I take the transpose of X times X, and then I invert that whole quantity inside there. So I take, again, the transpose of X times X first. Then the stuff that's inside this parentheses, the result, I do the inverse. And I take it times then the transpose of X times Y. So let's look at some matrix dimensions. Y is 20 by 2. Let me get a finer pen here. Oops, let's try that again. Fine tip pen, please. Yeah, that's better. This X then, when I transpose it, is going to be 2 by 20. I made a mistake here. This Y is actually 20 by 1. Now remember, X itself is 20 by 2. Let's actually come over here. 20 by 2. The transpose of X is 2 by 20. So the whole thing here is 2 by 2. So this right here is 2 by 2. Notice how the correct numbers that we need line up, and what I end up with is a 2 by 1 vector. So when I take the transpose of X times X, invert it, times X transpose times Y, I get this right here. Hopefully that looks familiar, because we actually saw those same numerical values in our introduction to R lecture. Specifically, they are the y-intercept and the slope from our regression model that we had found previously. So if you haven't had a regression course where they actually talk about it in the context of matrix algebra, this would be new to you. If you have had a matrix algebra course where you talk about it in the context of matrix algebra, you're very, very, very familiar with it. In fact, when I first had a course like that, my professor made all students repeat over and over and over again, x prime x inverse x prime y, x prime x inverse x prime y, because it's such an important result, and you need to know what it is when you do regression analysis. Okay, let's talk about two other things that you can do with matrices: finding the trace and the determinant. So again, we're going to be working with some square matrices. So let's let A be a square matrix. It's P by P in dimension now, just to be general. The trace of a matrix is very simple. Simply add up all the diagonal elements. That's it. The way that you denote the trace is with put a little TR, then a parentheses and parentheses there. To do it in R is very simple. There's actually not a trace function in R. Instead, what you have to do is take advantage of two other functions. In particular, let's say I have this matrix A, again, 1, 2, 3, 4 in it. And what I'm going to do is extract out the diagonal elements. And the way you do that is with the diag function. And then simply let's sum up all those elements that result from that. And the trace of this matrix is 5. So it's very, very simple. The determinant of a matrix, though, is maybe not as simple, but it's really not too bad. Let's look at it in the context of a 2x2 matrix first, because I think that's the easiest way to see it. So first of all, we denote a determinant by simply drawing lines around our matrix of interest that we want to take the determinant of. And so that's what I've done here when I write out the matrix in terms of its elements. Then the determinant is simply, you take the diagonal elements, you multiply them by each other, and then you subtract off the multiplication of the non-diagonal elements. We actually did this calculation when finding the inverse of a 2x2 matrix. For a 3x3 matrix, you do something very similar. You start with A11, and then you take the determinant of this part of the matrix. Then, do some erasing. You subtract then A12 times then the determinant of a matrix formed by these two vectors. And then lastly, take A13 times the determinant of that part of the matrix. So what you're doing is simply splitting up the 3x3 matrix into smaller parts, and then finding the determinants of these smaller parts, and then combining everything in a certain way. You can extend this to 4x4, 5x5 matrix, and so on. As you can see, the calculations aren't the most interesting in the world, so that's why we typically will use a computer. But again, it's important to know how to do in the 2x2 setting. So, using R, very simple. Here's my matrix A. To take the determinant, there's a function called det for determinant. There you go. Okay, our next topic is going to be about eigenvalues and eigenvectors. So again, let's suppose that we have a square matrix, p by p in dimension. Then we can define what are called eigenvalues of a matrix A as follows. I take my matrix A, and then I subtract off an identity matrix that's appropriately sized, where this identity matrix is multiplied by some constant that I'm going to call lambda. I take the determinant of the whole thing, set it equal to 0, and then I try to solve for this unknown quantity, lambda. So in the case of a 2x2 matrix A, we can find the eigenvalues, which are, in case I didn't say this, which are these values lambda. We can try to find these eigenvalues as follows. Here's my matrix A. I subtract off lambda times my identity matrix. Of course, with an identity matrix, when I multiply by lambda, that means that it essentially becomes a diagonal matrix with lambda on the diagonal. I do this subtraction, so I take A11 minus lambda, so I get A11 minus lambda. Take A12 minus 0, I get A12, and so on. Do some erasing. Then to find the determinant, I take then the product of the diagonal elements. I subtract off then the product of the off diagonal elements, and I should have a 0 there. Oops, I guess I don't need to have that, excuse me. Then I do some algebra, so I get this nice little polynomial equation written in terms of lambda. I set it equal to 0, and I solve for the possible values of lambda. You learn in your basic algebra class how to do this using the quadratic formula, for example. And lambda ends up being this expression here. This is for a 2x2 matrix. A, of course, could be, let's say, p by p in a very general sense. And what that ends up being is, happening then, is when you do all these calculations, you end up having to solve for the roots of a p-dimensional, you could say, polynomial. And so you would have p different lambdas, in other words, p different eigenvalues. Now, when a matrix is symmetric, the eigenvalues are all real numbers, and they can be ordered from smallest to largest. And this is going to be useful for us later in the semester. So often lambda 1 is going to be referred to as the largest eigenvalue. Lambda p is going to be denoted as the smallest eigenvalue. So let's look at how we can find these eigenvalues, these lambdas, using R. Okay, let me go back up. Oops. Okay, so I'm going to define my matrix A here. It's a little bit different from how I think we've seen it before. So I have a 1, 0.5, 0.5, 1.25. I'll actually see this matrix pop up later in the semesters. That's why I'm using it here. And to find the eigenvalues of A, I simply use the Eigen Function. And what's returned is a list. And we saw what lists were back in the introduction to R notes. Lists are, well, where we saw it was with respect to the LM function. What the LM function gave us back was a list of different items associated with the regression model. The Eigen Function does a similar thing here, where it gives us two different components, the actual eigenvalues. So this would be lambda 1, this would be lambda 2, and things called eigenvectors, which we will talk about shortly. Now, since this eigenfunction gives us a list, what we could have done is save the results from eigen into an object called save.eig, for the lack of a better name, and then we could extract then the eigenvalues out of that list by using this $ values part. Now, if we were to go use the by hand calculations that we saw from the excuse me, from the results from the quadratic formula, and make sure you can do this, one will see that one gets exactly the same eigenvalues as we get from the Eigen Function itself. So let's talk about what are eigenvectors. Well, each eigenvalue of A, so these lambdas, has a corresponding non-zero vector. Let's just call it B. It's p by 1 in dimension. And this is called an eigenvector, and it satisfies the following. If I take A times B, I get lambda times B. Now it's important to note that these eigenvectors, these B's, are not unique. So there are multiple eigenvectors for a single eigenvalue. When two eigenvalues are not equal, their corresponding eigenvectors are orthogonal to each other. In other words, in a geometric sense, you've probably heard of the term perpendicular before. In a mathematical context with vectors, that just means simply if you have one eigenvector called b sub I, take the transpose it, take it times then another eigenvector called b sub j, you get 0 back. Also, we have some interesting results with eigenvalues. And that is, if I take the trace of A, I get the sum of the eigenvalues. So that's kind of interesting. If I take the determinant of A, I get the product of all the eigenvalues as well. These are good proofs that you will learn about in the matrix algebra class. Don't worry about proving it for my class, though. So let's look closer at these eigenvectors in our example. Again, eigenvectors satisfy A times B is equal to lambda times B. And lambda is one of our eigenvalues. And so we just need to find these possible vectors of B that satisfy this expression. Two possible vectors are corresponding, first of all, corresponding to the largest eigenvalue. We have this as our first eigenvector, and corresponding to the second largest eigenvalue, or I guess also the smallest, we have this eigenvector here. Well, how did I do that? Well, one way is just simply to use R. So if I come back here to my output associated with eigen parentheses A and parentheses, I find my vectors here. So this first column corresponds to the first eigenvalue. So it's the first eigenvector. And the second column corresponds to that right there, the second eigenvalue. And make sure you can do this. You can actually verify that indeed when you take these vectors, these eigenvectors, and multiply everything out, that you do have this equality here, as by definition what an eigenvector is. And you can verify in R that indeed that this occurs too. So for example, with the first eigenvalue, lambda 1, we can take A times B, and notice what I do here. I extract the first column from this component of my list, do that multiplication, and then also here's lambda 1, the first component of my eigenvalues, and then here's also B right there, and notice that these two things match up. Sometimes you want to be concerned about what the length of a vector is. And so let's say that we have a vector B, that's let's say P by 1. Then the length of the vector is simply you take the square of all the elements in your vector, add them up, find the square root. If you haven't seen the length of a vector before, just think of it in the context of P equal 2, and using the Pythagorean theorem when you're dealing with finding the hypotenuse of a triangle. And that's essentially where that idea comes from. Now, the reason why I bring this up about the vector length is that R chooses eigenvectors that always have a length of 1. So just to verify that, let's look back at our eigenvectors once again. So I'm going to extract the first eigenvector. Then what I'm going to do is square each element. And let's sum these elements. And if I were to take the square root, obviously in this case I wouldn't necessarily need to, but I get 1. So the length of the vector is 1. Well, let's see this graphically then. Let's actually skip ahead to the plot, and we'll talk about how I got the plot shortly. Here's a plot of my two eigenvectors. So my eigenvectors, let's call it B, has two components, B1 and B2. I'm going to put B1 on the x-axis, B2 on the y-axis. And the way that you typically draw vectors is that they come out from the origin. And so in our particular case, the first eigenvector was 0.61 and 0.78. So here's 0.61, here's 0.78. And so I drew a vector. Notice I actually put little arrows there out from the origin. The second eigenvector comes out to this point right here, and we can see how these two eigenvectors form a right angle. This means that they are orthogonal to each other. They are perpendicular to each other. But again, these eigenvectors, though, are not unique. So these are eigenvectors of length 1. I could have length of 2, 3, 2.5, 10, and so on by simply multiplying the elements of the vector by the length desired. Try it on your own. Let me do some erasing here. Okay. Also, I want to point out the following, that if I formed a triangle here, you see the length here is 0.6154. The length here is 0.7882, corresponding to the elements in the vector. If I were to multiply, if I were to take 0.6154 squared plus 0.7882 squared, that's going to be equal to, let's call this C squared. And so then so you can see how the length of the vector comes about through a direct application of the Pythagorean theorem. Okay. Well, how did I get this plot? Yeah, actually come over here to 10. First of all, I want to draw this plot in a way that my x-axis and y-axis are exactly the same length. Okay, and one way to tell me to do that is to use the par function. This stands for graphics parameters. My plot type is going to be squared. So if I just highlight that code, up will pop up my window, and anything that's drawn in there is going to have a square plot to it. And then in order to draw my plot, let me just simplify this first, and then I'll explain the other components later. I need to set up a range for my x and y axes. They're kind of, let's say, dummy values. So I'm going to create something that allows me to go from -1 to 1 on both the x and y axes. I'm going to plot those points, but I don't want to actually plot the points themselves. I just want the, you could say, the xy axis. So I have type equal n for no, don't plot it. And this is what I get. Try it without the type equal n. See what happens when I don't put the no or the n there. Okay, so now I need to plot some stuff inside of there. Or actually, let me show you this here. I did some more fancy things with respect to putting a title on my plot, x-axis labels, y-axis labels, all using the expression function. You can get into that more if you want to. Just do that. Also, I put some grid lines on the plot to help us see everything. Next, what I'm going to do to help us see stuff too is I'm going to plot a horizontal line at 0. So the AB line function with the h argument set equal to 0 plots a horizontal line at 0. It's going to be solid. And the width of the line is going to be 2. So twice the regular size. I'm going to do a similar thing for a vertical line. Let's see what happens. And so you can see those dark black lines there now in the plot. And lastly, to actually plot then the vectors themselves, I use the arrows function where I start from the origins. So it's like taking 2 points in space. Let's call the first one x0, y0, and the second one x1 and y1. I'm going to draw from the origin out to the 2 parts of my eigenvector. I'm going to color the eigenvector in red and use a solid line type. This is the first eigenvector. This is the second eigenvector. And there you go with your plot. So it's not too bad. And again, I urge you with plots like this that have multiple components is step through it like I did here to see what happens if you include something or if you don't include something. That's how you learn how to do these kinds of plots. Okay. And lastly here, let's talk about positive definite, positive semi-definite matrices real quick here. Simply put, if you have a symmetric matrix and all the eigenvalues are positive, then the matrix is called positive definite. So just a nice name for it. If you have exactly the same thing, but at least one of the eigenvalues is actually 0, then you have a positive semi-definite matrix. And if you either have a positive definite or positive semi-definite, you have a non-negative matrix. This matrix A that we saw before was positive definite because all the lambdas were greater than 0. All the eigenvalues were greater than 0. If you've heard of covariance matrices before, again, a covariance matrix is always at least positive semi-definite. Most of the time, you're going to be working with a positive definite matrix. So that concludes then this little introduction to what matrix algebra is. If you have any questions, please feel free to contact me and ask your questions. Thank you.